in our previous class we have studied about the isomerism, and then we studied about stereoisomerism. Okay, we studied about the different types of stereoisomerism: configurational isomerism, and in it we have studied about geometrical isomerism. We have taken the example of geometrical isomerism, and then we have taken examples of optical isomerism. Then we have got an introduction with conformational isomerism. In this video we are going to learn about the first kind of stereoisomerism, particularly the configurational isomerism, which is optical isomerism. But before delving into optical isomerism, before understanding the phenomena of optical isomerism, we must understand the few concepts. The first concept is the concept of plane polarized light. In short, we call it PPL, plane polarized light. Now you all know that a normal light is the one which is having vibrations in all plane. Light is a wave. So due to the property of wave, we are considering it as vibrating wave, which has vibrations, which has some kind of frequency. So it has vibrations, and these vibrations travel in all plane. We can assume it like this is the source of light, and it is sending light in all directions, in all planes. So obviously light is going in all planes, so it clearly means that the vibrations that it has, it will be again lying on all the plane. But if you pass this normal light through a special kind of crystal called nickel prism, I can represent it like this. So we are having a normal light and we are passing it through a nickel prism. Okay, let me give you a more easy structure like this. Okay, let us consider this. Okay, we can consider it like this. Okay, we are passing it from a prism, nickel prism. Now when this light is passed through nickel prism, its vibration in all of the planes are cancelled except the plane of axis of nickel prism. Only those vibrations are left which are along with the axis of nickel prism. As because all these vibrations are only in one plane, such kind of light is known as plane polarized light. You can understand the concept of plane polarized light by a simple analogy, that if a rope is attached to a wall through a slit like this, this is a slit, and this slit is vertically aligned, this is a vertical slit. So you can only wave it in the vertical direction. You can wave this rope only in the vertical direction. So vibration will be only vertical. If you try to vibrate it, say in horizontal direction, these vibrations cannot happen. This vibration get cancelled because the vibrating rope will directly hit these surface. Only those vibrations which are parallel to the vertical slit will pass. Take another example. Say a man is passing a door. He will only pass it when he is in the vertical direction. If you try to pass this man horizontally to this door, it will definitely not pass. It is not possible. So in the same way, this is a normal light. It has vibrations in all plane. So when it is passed through nickel prism or tourmaline crystal, the vibration in all the other planes are cancelled except the one which are here in vertical direction, or you can say which are parallel to the axis of nickel prism. And now the outcoming light is the one which is having vibrations in only one plane. This kind of light is known as plane polarized light. So in practical sense, the plane polarized light looks similar to that of normal light. There is no difference. Difference can also only be understood, observed when you are having a Polaroid glass. So this light is very important to understand the optical isomerism. Now, when this plane polarized light, this PPL, plane polarized light, is passed through a special kind of sample which is known as optically active. There are some chemical compounds which are optically active. What are those compounds? These compounds are those through which when PPL is passed, the PPL either turns in the right direction, either rotates towards the right hand side, or there are some who are able to rotate this PPL towards left hand side. So either the PPL, plane polarized light, is rotated towards right or it is rotated towards the left. The PPL which is rotated, if rotated towards light, the optically active compound is said to be dextrorotatory. Dextrorotatory. It is represented by small d, or you can also represent it by the symbol, by the sign plus. If optically active compound rotates it toward left direction, then the sample is said to be levorotatory, or small l, or you represent it by the negative sign. If a compound do not rotate, if a compound does not rotate PPL in any of the direction, then simply this compound is optically inactive. Okay. Now if there is a compound which is dextro, if there is an optically active compound which is dextrorotatory, then surely there must be another compound which is levorotatory. If A is dextrorotatory, then definitely there will be another compound B which will be levorotatory. And obviously these two will be isomers of each other, and these two are optical isomers. Optical isomers are also called as enantiomers. Got it? Now, as you can see that optically active compound can be identified by its ability to rotate plane polarized light towards right or left. Right rotating are known as dextrorotatory and left rotating are known as levorotatory. If there is a compound which is optically active, it will always has its isomer. Means if there is one which is dextrorotatory, there will be definitely another molecule having same molecular formula, same structural formula, but different orientation in 3D space, which would be levorotatory. The example which I gave you in the previous video was like this. There was a compound in which carbon was attached to chlorine and OH group by a single bond lying on the plane of paper, and there was an H going above the plane and there was one CH3 going below the plane, and there was another isomer, and let us take it that this compound was optically active and it was moving the plane polarized light towards right. So certainly it's mirror image. Certainly its mirror image is the second compound which is levorotatory. Okay, you have to bear this in your mind that if the first compound is dextrorotatory, then obviously its mirror image will be levorotatory. If dextrorotatory is present, then certainly there will be a levorotatory, and these two compounds will be optical isomers of each other. Say if this compound is levorotatory, then obviously its mirror image will be dextrorotatory in that case, but both will exist, and these two compounds are optical isomers of each other. They are also stereoisomers, and you must remember that optical isomers are also known as enantiomers. Okay, coming to the practical aspect, after the light is rotated towards either left or right, it is again passed through a Nicol prism. Now obviously the plane of light has been rotated and it is not aligned with the Nicol prism. So if there is a person on this side who is watching through this prism, he will not be able to see these light until the plane of light, until the prism is moved in such a way that it is aligned like this. It is aligned, its axis is aligned to the plane of the PPL, right? So you have to move it, you have to rotate in such a way this prism that either towards left or towards right, that depends upon dextrorotatory or levorotatory the compound is. So you have to move it, rotate it in such a way that this light, the axis of Nicol prism, becomes parallel to the plane polarized light, because only in that case the light can pass through the prism and can reach to your eyes, and only in that case you will be able to see the light. So how much you have rotated, how much degree you have rotated the Nicol prism will give you another parameter which is known as angle of rotation. The first Nicol prism which converted normal light into plane polarized light was known as polarizer, and the second prism which was helping to identify the degree of rotation is known as analyzer. So there are two prisms which are used in this instrument. This complete setup, this complete instrument has a name and it is called as polarimeter. So polarimeter is the one which can tell us whether a compound is optically active or not, which means whether the compound rotates plane polarized light towards right or left. Okay, so polarimeter is the instrument. So you must all remember what polarimeter is. Let me see this point. Let me revise this point, that you have a plane polarized light, okay, and it has been passed through a sample, and let us say that this sample has rotated this light at 30 degree and with a positive direction, that means towards right. That means your sample was dextrorotatory, and in order to see it through your eyes, you have to rotate the analyzer to 30 degree as well, because only in that case these two lines, these two axes will be parallel to each other and you will see the light. The angle through which this analyzer has been rotated is known as angle of rotation. Angle of rotation is usually denoted by theta. Angle of rotation is represented by theta. Now this angle of rotation depends on some factors. You must understand this, you must recognize these factors. The first factor is it depends on the nature of optically active substance. Okay, it depends upon the nature of this substance in the sample, okay, whether it is optically active, how much it is optically active. Second, it also depends on the concentration of the sample, concentration of the optically active compound. Okay, this sample is usually represented in gram per ml. You must remember this unit, it is very important. The third factor on which the angle of rotation depends is the path length. Means it is the length of the solution through which the light passes. Means the width of this sample, because say for example your sample is kept over here, okay, you have there is a sample tube usually between polarizer and analyzer. So you have there is certain kind of length. There is a tube in which you keep your sample solution in the polarimeter. So the length of this tube has a great importance. The length is usually represented in decimeter. So you have to remember that this length has to be it is represented by L and its unit is in decimeter. So the length when changes, it will also change the angle of rotation. So third factor is again very important. It is the length of the solution. You can also simply say it as path length. Okay. Fourth factor on which the angle of rotation depends is the nature of solvent. Nature of the solvent. Solvent means, say if your compound is it's a solid, so obviously if you want to make it in the solution, you have to introduce a solvent, and you must remember that this solvent must not affect the optical rotation. It must not be optically active. It must not affect the angle of rotation. So nature of the solvent is a very important point to be taken care of. The fifth is wavelength. wavelength of monochromatic light. See, the light which we were using previously, it was normal light, then it was converted into PPL after passing through polarizer. The wavelength of this light, the lambda of this light, has a very big importance. There is a term which I have written is monochromatic. Monochromatic means, chroma means color. So monochromatic, the term monochromatic means of having single color. Mono means single, only one. Chroma means color, only one color. Technically it means only one wavelength, one lambda, one wavelength. Okay. So monochromatic light is that which is consisting of only one wavelength. Normal white light, you know that it is consist of Vibgyor. Normal white light consists of 7 colors Vibgyor. They are having 7 colors, and along with it there are having so many wavelengths between them. But the monochromatic light will have only one wavelength. That is why it is called monochromatic. Okay. So it also, the angle of rotation theta also depends on this lambda as well. Usually the lambda which is taken, that which we take, is lambda for the D line of sodium, okay, which is basically 589.3 nanometer. So we usually keep this wavelength fixed at 589.3 nanometer. Okay, and the last thing on which the theta depends is the temperature of the sample. So there are 6 points on which this plane in which the angle of rotation depends. Temperature is usually taken around 25 degrees centigrade, basically usually 20 degrees centigrade, which is 293 Kelvin. Okay, so these are the following 6 factors on which the angle of rotation depends. If you change any of the factor, the angle of rotation will change. Now you can ask me that, sir, what is the importance of studying angle of rotation? Okay, we know that there are some samples which convert PPL, plane polarized light, to a certain angle towards right or towards left. So what is the value of this angle of rotation? Now I can say that out of these 1 to 6 parameters, if you keep them all fixed, out of these 6 parameters that you have studied here, if you keep them all fixed, the theta will also get fixed, and by this theta you can identify the sample. Now when all these parameters are fixed, then this theta is actually not called as theta, it is called as alpha, which is known as a specific angle of rotation. Now what is specific angle of rotation? Specific angle of rotation is a parameter which will help you to identify whether a compound is, you can identify it, you can know what compound is by just knowing its specific angle of rotation theta. Okay, now the alpha, the specific angle of rotation, is represented by this formula, alpha dt. Small t represents the temperature, capital D represents D line of sodium. 589.3 nanometer. It is equals to theta upon L into C, where theta is the observed angle of rotation. Okay, rotation. L is the path length and C is the concentration. Remember that this L path length is measured in decimeter. This C concentration is measured in gram per ml. The D line of sodium is 589.3 nanometer and temperature is 293 Kelvin. Now, what will happen practically is, I will give you a sample and I ask you to identify what this compound is. So you will put it in polarimeter in front of nickel prism. This is your polarizer. Normal light will get converted into PPL. PPL will pass through this sample. This sample will turn the plane polarized light, say, towards right. Then you will check the angle of rotation theta with the help of analyzer and you will get theta. Now you will put the value of theta in this formula. The concentration is known to you, the path length is known to you, it is fixed in the instrument. This D is also fixed in the instrument. You also know the temperature, and by keeping in this formula you will get alpha, which is specific angle of rotation. Now you will take this alpha and you will see in the reference to which compound this alpha belongs, and you can easily identify the sample. So this is the whole process. Now how will you define alpha? Say you have the formula alpha T D is equals to theta upon L into C. Okay. Now if L is 1 decimeter, if C is 1 gram per ml, then this implies that alpha in that case will be theta. Now this is the way to identify define a specific angle of rotation. Okay, so specific angle of rotation is defined as the degrees of rotation observed. Okay, this theta was observed, so it is defined as the degree of rotation observed when plane polarized light is passed through a sample of path length 1 decimeter and concentration of 1 gram per ml at a specified temperature and T. Okay, so specific angle of rotation is that observed angle of rotation which is taken when the path length is 1 decimeter and the concentration is 1 gram per ml. So if you tell the angle of rotation keeping L and C as 1 decimeter and 1 gram per ml, the observed angle of rotation will now be called as specific angle of rotation, and this can identify the sample. Okay, so specific angle of rotation is one of the intrinsic property of a compound, of an optically active compound. Yes, optically the compound has to be optically active in this case, and this is a very important parameter in stereochemistry. So you must all know what this is. Okay, so in our next video we are going to study the concept of optical activity, but before that you have to learn all these concepts. Okay, now we will start this optical activity in the next video. Thank you so much.